So this is x, yeah. Yeah. So this is our explicit formula. You can call it, I mean, it is equivalent to having the prime number theorem. So this we put back now. Okay, we have this estimate, which we know that so it uses with whatever you like. You can use the Siegel-Waldface or the prime number theorem in arithmetic progression, whichever form you want to use it in. The idea is to bound it. Okay, so this should not have been rubbed out. Okay, you still have it on paper. So now I'm going to put this back here, this bound. So which was a pink star, yeah, over there, but I rubbed it out. So in this pink star, okay, what do we get then? Yeah, in what does it mean? Using the explicit bound formula, which is there in chi, in star, we get then sum of chi of k, lambda of k, exponential k beta. So bound it now, and you get big O of 1 plus beta n exponential minus c square root of log n. This is my bound, which comes from there. Okay. Now here, chi was not chi 0. Okay. So the case where chi is equal to chi 0, if chi is equal to chi 0, then I'm going to write psi of so I take a precise value of this x at so u chi 0, and this is equal to u plus r of u, where r of u, what is it equal to? It's big O of exponential minus c log of u. Okay. So from the prime number theorem, I know that just the prime number theorem, here I don't need any chi. I know that psi of x is equal to x plus big O of x exponential minus c log of x. Yeah. So what remains to be calculated now? What did we have here? So we had exponential n beta psi n chi. Yeah. So now I will use a notation. This is probably Vinogradov's original notation. I think so. So here we are, and now we move to the next one. We introduce notation T of beta, and this is equal to exponential K beta, or K going from 1 to n. Okay. And I want to say something about this. Okay. So we use summation by parts, something that you know how to do. And what do we get? T beta is equal to, so exponential, the big term is n beta, get an n for that, and minus 2 pi I beta 1 to n exponential u beta, and then this one comes back here, this one. Du. Okay. We are in this case, chi is chi 0. Okay. So now I want to calculate chi 0 of k in the original formula that we had stopped at. So we will just introduce this T of beta. Okay, it's just a notation. So sum of chi 0 of k lambda k exponential, this is my exponential k beta. What is this equal to? This is equal to T of beta, which is this, okay, just defined here, plus exponential n beta r of n minus 2 pi I beta. Then I have this one in the integral, e to the power here, this one, eu e yeah, that's okay, exponential u beta r of u du, and that's equal to T beta. So the idea was to separate out T, and we have done this, big O of 1 plus beta n, that's what we get from over there, n exponential minus c squared of log n. Okay. So this T of beta, you can subtract it from the original formula, and then this one does not come into the scene anymore. So S of alpha is going to be yeah. Yeah. Hmm? Who should be there? You. In psi of x? No. Where? Here? R of u? Yeah? Ah, yes. Yes, yes, yes. X from this one. Yeah? So, what should we do now? Now we subtract this t beta, which so subtract t beta. And then you get, if you subtract t beta to get S of alpha, this is equal to 1 by phi q tau chi 0 t of beta. There'll be not enough space here to write. So, okay. Multiplied by t of beta plus big O of, I'm just copying from there, 1 plus beta n and n exponential minus c square root of log n. All right? There should be, okay. And now there's this one term, and the other term is plus sum of tau chi bar, chi of A into error term, say O of 1 plus beta n exponential minus c square root of log n. And a second bracket here. Okay. Now, from Gauss sums, you know, or if you don't know, we can believe it. I don't remember whether we actually use this ever or not. So in this formula that we have written over here, yeah, see, you have this tau of x0 here, and do you know anything about this tau of x0? I'm saying recall, but I don't know if we didn't do it, we can do it. It takes really very little time. Tau of chi 0 is mu of q. Did we ever do this? I don't know. However, we did do this I remember. Tau of chi is bounded by this, we certainly did, is less than equal to q to the power half. This one we certainly did. Whether tau chi 0 is equal to mu chi we did or not, it's easy, can be done. All right? Yes, after tau q0, the There is a bracket here for this one. You mean there should be a third, another bracket? Yes. So there's no place to put another bracket. Yes. Which last sum? Yes. This is where chi is different from. The two things. One is when we have equal to chi naught and when we have different from chi naught. So for chi naught, we know that chi of chi naught is mu q. We can do that if you like sometime. And there's a bound for tau of chi. This is for chi mod q. Yeah, this we did. So I'm pretty sure we did this. Okay. So now I go back and calculate, because you are all very strong people, you know how to calculate a lot of things, and so you do it. So you get S of alpha is equal to, so I'm going to use this for tau of the Gauss sum for chi 0. This is going to give me mu chi, and so I have mu chi, mu q for that one, then phi q from here, okay, and then you have T beta. You agree with me? There is this T beta which comes back, and the rest of the things we will send into the error, okay, which is 1 plus beta n, okay, need some space. Okay, into n exponential minus c square root of log of n, and plus the second term here, tau chi bar, chi of a, to O, big O of 1 plus beta n exponential minus c square root of log n. All right. I think I did something false. T of beta plus, no, where are all these? All of that will get eaten up by the error term. Yeah, so that's not correct. This, what I wrote is not correct. The first thing is correct. O plus, big O, 1 plus, I get the beta, the n, that's fine. And then I can use this. I haven't used it yet. So here, let me use it. Q to the half. I mean, why did I write it if I'm not going to use it? And then that's eaten up by the rest. The error term. So now, remember, where was our alpha? Where was alpha? Yes, but a major arc. Yeah, alpha is in the major arc. Therefore, since alpha is in the major arc, okay, since alpha is in the major arc, since it's in the major arc, I can use my construction of major arc, okay? So Q is, I've taken all Q which is less than equal to P, and my beta which is less than or equal to 1 by Q. Remember, this is how it was constructed. Where should there Q to the power half and then an N? Yes, okay. People listen. So beta, this was the construction of our major arc, remember? So I am allowed to use them. I mean, if not, why did we have them? So S of alpha now, therefore, is equal to, keep it back again, mu Q, phi of Q, T of beta, plus, and big O, yeah? And now, since Q is up to P, this whole thing, this becomes N. I have Q up to P and beta bounded, so I use the bounds for them. I'm left with an N and exponential. Exponential minus C log of N. All right? So what do you notice? Okay, maybe you're tired of all the calculations that I'm writing out, but what has happened? Philosophically, what has happened? Why did we make this huge effort? What really has happened that is good now? The error term has become smaller. There's an improvement on the error term. Okay, all this was not done for just because we are bored with life, we don't know what to do. There was a motivation for doing it, and we have done it. Okay, so that's the remark, is that the error term has been removed. So this is a better error term. Okay, this is a better error term. So now remember what was, forgetting all these calculations that we did, what was our initial, let's go back to thinking what we wanted to do. What did we want to do? We have 3 primes. And then we have S alpha, and then we want S alpha cube. So now we will go, we are not afraid. We will go and cube this whole thing up. Okay? You are not afraid, are you? No, you're not afraid. You're not afraid just of a little cube. So forget everything and remember now just that we have got S alpha is mu alpha phi, mu q phi q t beta, and a reasonably good error term. Okay, that's what all this did till now. And now you want to take a cube of this alpha. So S alpha cube, or let's put the cube here. So cube it now. So mu q, you're not going to write mu q cubed, I hope. So phi cube, which is cubed, t beta, which is cubed, okay, plus error term, big O, so n becomes n cube, exponential minus c square root of log n. All right. So now we are on the major arc. What we have to do now is to integrate over the major arc. So let's do it. We take an integral over the major arc, AQ, okay, S alpha cube exponential minus n alpha d alpha. All right. What is it? We write everything back. It's since mu of q, okay, mu of q, phi q, phi q. You have a problem? Do you have a problem? Phi q cubed exponential minus an by q. And then my integral, because I am over aq in the major arc, therefore my beta is between is less than or equal to 1 by q. So I can move my integral between minus 1 by q and plus 1 by q. So since I'm here, I'll move it between minus 1 by q and plus 1 by q, t beta cubed, all right, t beta cubed, exponential minus n beta, d beta, plus big O, and the big O is now n square exponential minus c square root of log n. All right. Now you're going to sum over all the major arcs to get the whole sum over the, or which is over all, to get sum over m. Okay. So here you have over a and q, but you want the union of all a and q. So what's going to happen? You sum it now. So summing over all major arcs, because I have to sum over them all. It's not enough to take it over one major arc. Okay. Then my integral becomes, okay, over all m, s alpha cubed exponential minus n alpha d alpha. So use the properties now of what we know, that what happens when we are on the major arcs. So this is the sum of all q which is less than p, the p that we took in the beginning, from our sieve, mu of q divided by phi q cubed, phi q cubed, and then you have the rest of the things which come from there, exponential an by q, the sum of this, a going from 1 to q, a and q co-prime, and the integral which is between minus 1 by q and 1 by q. Okay, of t beta cubed. Okay, t beta cubed exponential minus n beta d beta. What remains is an error term, that's big O of n square. That's the one, n square exponential some constant. Maybe I haven't been very good with the constants. I've kept them always C. Maybe I should have called them, change the name sometimes. And what's the inside sum now? Does this exponent, does this ring a bell? This part? Does it ring a bell? Exponential an by q, a1 to q, aq is 1. It's similar to the Gauss sum. And in fact, this is, you remember that in the first class, we said that there were a family of such sums. One special case was the Gauss sum. So this is another special case, and it has a name. So somebody knows the name? You know that? Yeah. So this is called the Ramanujan sum. Okay. Everyone has, of course, heard of Ramanujan, I suppose. Yeah. Have you? Have you heard of Ramanujan? So, yeah. I even went to see his house, the same house where he died in the same house where he was born. It's a small house in Tamil Nadu. But yeah, that apart. So this is the Ramanujan sum, yeah? So sum of exponential an by q where a goes from 1 to q and is co-prime to 1. This is called the Ramanujan sum. There are some properties, I mean, since we didn't study it specially, there are some properties that we can look at in an exercise class. This Ramanujan sum is multiplicative, and it can be, so properties are, this is multiplicative. It can actually be evaluated at each of the, so CQ of n, this is equal to d mu of q by d, d divides n, and d divides q. And CQ of n can be bounded by phi of q trivially. Okay, we can do these small things when we are tired. Yeah, so CQ of n, therefore what am I trying to do? I'm trying to get this mu q phi q divided by phi q cubed, and then I have this Ramanujan sum. So let me try and estimate this. Okay, so summation q greater than p mu q phi q cubed. This one, let's give it a name, CQN. Okay, so CQN, this is equal to, write out the definition, product of little p, 1 minus P of n, p minus 1 cube. Can you guess what's going to happen now? Things are you trying to see the end of the story? Can you somehow see where we are going? The end of the story, you know, when the murder mystery is coming towards an end and you have to find who has done the killing. So you see these things that are landing up? Yeah? These are going to give me my singular series at the end. Yeah? So P 1 minus Cp NP, and that's equal to product of P dividing N, 1 minus 1 by P minus 1 square. It's exactly, we've come to where we wanted to come. P does not divide N, 1 plus 1 by P plus 1 cube. And that's, what is it? This is equal to S of N. You remember right in the beginning we stated this, and you have certainly wondered, where is this funny thing, this singular series coming from? It's looking like zeta, yeah? So it's actually S of N. Yeah? Capital N, I think. All right? So take it back. Take it back into your initial. Okay. So, yeah, here, over there. We have got this. And then, so I can write again. I'll just write that mu by q. Mu q phi q cubed cq of n, little n, cq of little n. Is it little n? No, this was big N, yeah? So this should have been capital N. CQ of capital N, it's the limit. And this is equal to big O of log to the power something b plus 1 n. Remember what we said? We are going to get a b, and this b we are going to choose in terms of the a which we had in the beginning of the theorem. So I still have a bit to do before I finish the measure arc, because I still have to calculate T beta. Yeah. So yeah, maybe we can do that in the second part. Yeah, we keep it like this. And I've almost finished. You can see that I've almost finished, but not really. So I need still to evaluate T beta. Okay. And once I evaluate T beta, the major arc part is done. And I told you the major arc part is really where we do not cheat. We use everything that I have used today is everything we have already seen. I mean, there's nothing that has just said, yeah, it's like that. It's not like that. It's exactly something, and we have seen that. In the minor arc, we'll go fast because we will not go into the exponential sums. We won't have time to do everything, all the details. So the major arc, I'll finish after lunch. Is that okay for you? Or you want it just now? Then we won't have time to come back for, we have to go for a talk also at 2 o'clock. Yeah, so we have to go back and get lunch and all that. So I will finish it afterwards, okay?